Good morning. Today I am going to give you a demonstration of a software tool, Advanced Design System. Using this is a very higher and industry level software tool for designing the RF and microwave circuits. We'll see how to use this tool and create some small experiments such as impedance matching and transmission line calculators. So first to start with this, I'm opening, you can download the ADS design system student version and you can install in your computer and you will be having your icon on the desktop. Open the ADS software. As soon as you open, you can find this kind of window where you have the lot of options in the top. In that you have to go to file. So before I start any of my design, I have to create a workspace and inside the workspace I have to keep all my schematic files. So I'll go to new. Under new, I'll go and click on workspace. So when you click workspace, by default there is some name assigned by the computer, my workspace 18. I'll change that to matching. For example, I'm going to doing this. I'm going to do some matching circuit experiment. So I'll write as matching underscore work. Underscore work is the extension for the workspace. And default it will be stored in C users U, the computer name. So now create workspace you do. As soon as you click create workspace, a new window will be coming here. In that window, we are going to see our workspace what we have created is found. Okay, and you see in the top you can find so many things. That the first one is the create a new workspace, second one is open a workspace, then this is nothing but the started window, get started window, example library, and this is a schematic window, layout window, and any symbol you want to create, that symbol window, and this is a data display output window. So now I'll go to a schematic window. Under the workspace, the first design what you're planning to do, I'll be going for creating a schematic and start to work on it. So I'm going to design one lumped matching circuit. So I'll write the name as lumped matching circuit. You can give any name. Create schematic you do. As soon as you click create schematic, you can see one window is opening, the schematic window is opening. So this is a schematic window what it is opened in ADS. So now I have so many things here, icons are shown here. You can just go and keep the cursor on every icon, that description will be shown there. So in that we will be continuously using few important icons for our design and simulation. And we have a library here. This library will be consisting of all the components. Uh, it holds all the simulation controllers as well as power supplies and all the lumped as well as discrete and transistors, all components will be present in this. So I'll go to lumped components and I can find all the resistor, capacitor, inductors and ideal blocks available. And you can scroll down this and see so many options are there. Under sources frequency domain, I can find all the power supplies. So generally I'll be using one DC power supply, AC power supply and one tone input. Okay. So now I can have all these things here. So you can select and check for everything. Simulation HB, you will be having a simulation HP, then simulation S parameter. Under simulation S parameter, I can have some S parameter simulation components. Under simulation HP, if you check, you will be having simulation harmonic balance components. Okay, and you can come to simulation DC, in which you can perform some DC simulations. So if you come to the transmission lines here, okay, in that I can find all type of transmission lines. So ideal transmission lines, microstrip transmission lines, strip line transmission lines, waveguide transmission lines. So you can open and check all the options. And if I want to select some active devices, for example, I can go to devices BJT, then devices JFET, devices GasFET, all this will be available. And any filters I want to have, I can have the filters also. So this is all the component description. So now I'll go and explain you how to select some basic components and construct one circuit. So for example, I want to construct one matching circuit. So your matching circuit basically made up of lumped. I'm designing a lumped matching circuit. So in that case, I can select one capacitor, one inductor, and capacitor I'll put it in shunt. I'll put as rotate. I'll keep the capacitor here and I'll join it with the wire. The wire is there in the top. You can click on the wire and connect it. And now how do I terminate this circuit is I'll go to simulation S parameters. In that I have terminating resistors. This is called as terminating resistor. I'll bring and place the two terminating resistors. One is term 1, other one is term 2. I'll join these two terminating resistances. Okay. I'll join like this both the sides and now I have to ground this. So you have a ground option in the top. Click on the ground and place it everywhere so that the circuit will be completed. So this is one simple, this is nothing but one small matching circuit design. So this is nothing but a matching circuit design. So you can construct the matching circuit design, this kind of configuration and this one. I can do it using a tool called as Smith Chart Utility tool in the ADS software. So where do I find the tools is I'll go to tools. Here if you see there are a lot of tools available. In that we have a line calculator tool, we have a Smith chart tool and even there is an impedance matching tool. I'll go to Smith chart tool. So as soon as I see there is a one window open which is called as a Smith chart tool. So in this if you see the red color circles which is forming here is nothing but the Y circles, admittance circle. The blue circles are nothing but the resistance circles. And as soon as I see this window, what are the first things I have to observe is what is the frequency of operation for my matching circuit and what is a Z0 for my matching problem. That I should always check this and first only update it. Without updating this, if we directly start creating one matching circuit, then that matching circuit will be working for this default frequency of 1 gigahertz and Z0 of 50 ohms, but you might be having a problem statement different and the matching circuit you need to generate maybe for some other different frequency. So kindly check first whether this frequency and Z0 is updated. Then later if you come to this, there are three small windows are there. One is a Smith chart window, other one is a graph window here where I can see the response of the matching network what I am creating, and this is another one is a network schematic. So I'll generate a network schematic. This network schematic I can again reconstruct in the schematic window and check the output response. So now for example there are two impedances shown here, one is ZL, other one is ZS star. So ZL and ZS star now both are here only. Now I'll go and apply what may be my output impedance. Let the output impedance be 50 plus J0 only. I'll fix to 50 ohms and the frequency I'll change it to some 5 gigahertz. Okay, when I change this to 5 gigahertz, then my stop frequency here, if you check it is at 2 gigahertz, then that stop frequency should be greater than the frequency of operation what I'm setting generally. Okay, so since my design frequency only is 5 gigahertz, if I see the response, I have to have for some more frequency, so I have to take this as 8 gigahertz, okay, or 10 gigahertz. It should be greater than 5 gigahertz. So now you come back to ZS star. ZS star is the one which I will be giving some different input impedance. So when my input impedance is 100 plus J10 for example, okay, I'm having ZL as 50 ohms and the ZS as 100 plus J10. That is my problem. But actually when I go for feeding the input in the impedance Smith chart utility tool, I have to give the conjugate of the ZS. So 100 minus J10 I will feed. Okay, because we know already that there is a concept called as conjugate matching or maximum power transfer. So I will be able to get a very good maximum power to be transferred from input to output only if I do the conjugate matching. So conjugate matching is basically nothing but ZL is equal to ZS star. So I have given 100 minus J10. So when I press the enter, you can see the location of the source impedance and this middle one is the load impedance. Why the middle one is load showing in the middle is because since I have chosen 50 is my middle point of the Smith chart. So now how can I construct this Smith chart matching network for these two impedances? I'll go on. I have to move from my ZL, okay. From ZL I have to move to ZS star. So what possible ways I can follow is, I can go up in the resistance circle and come down in the admittance circle. So if I want to go up in the resistance circle, according to theory, I have to choose a series. Okay, I have to choose a series. I think the circle is forming faster. Escape. So you see, select the ZL. I'll give escape. I'll start from the beginning. ZL. I'll press this. Okay. I'll go for series shunt. Shunt, it is passing. See the path what it is followed in this video. It is following the downward. It's following the upward path, but it is going up in the conductance circle. But I want to go up in the resistance circle. So if I select this, you see it's going up in the resistance circle. Till this point I'll move. Then after that I have to come down in the conductance circle. So for coming down in the conductance circle, I think I can use a series capacitor. So you see that is moving down. So you can come and place this point. So when I come and place this point, see the response, how this response is changed, become a broadband response, and it is resonating at one point here. And what is the values, the network formed? One series inductor and one shunt capacitor. So series inductor, if I click, the value shown is, it's showing as 1.638 nano Henry. And what about the capacitance value showing there on the screen? It is 633.51 femtofarads. So I will note down this and you can save this window. Now you come back here. So what is the configuration of this? You please check once. From the ZL side, I should have first an inductor, then the capacitor. So now I'll just cut this. I'll move this here and I'll place the inductor here. Okay, so I'm placing the inductor next immediately after the ZL. So you can connect this like this, and again this one here, and this also is connected. So now what is the values of L we saw from the Smith chart tool? The L what we designed is something ranging between 1.63 nano Henry. So go back here. So you come back to the circuit. It is 1.638 nano Henry. And what is the capacitance value we saw in that Smith chart utility tool? It was 363.51 femto. This femtofarads. And what about the impedances? Fine. The impedances, you see, one ZL is 50 ohm, but what about the ZS? I selected as 100 plus J. You have to give star also for this, otherwise it will show error. Star, it was 10. But actually we fed the conjugate value of this there, but I am not supposed to enter the conjugate value in the actual schematic. I'll be entering as plus J10 only. So now I have completed my matching circuit. Whatever I have designed here, the same thing I have constructed in the schematic. So now what is the next thing I'll do is I'll go to simulation S parameters. In that I will take and put the S parameter simulation, because I am going to do the S parameter simulation for this matching circuit. So what is the start frequency? I'll start, because I'm designing this for 5 gigahertz, no? So I'll start at 1, I'll end at 10, and step of 10. Let it be the same thing only. So once you form this circuit, you save the circuit once, and then you go to simulate window in the top, and you can simulate like this, or you can go to the simulate icon directly here, click on the simulate icon. So when you click on the simulate icon, there is one screen which is running, showing you what are the steps it's following. Any errors coming, it will display. So there is no errors. As there is no error, there is another data display window opened, which is the window where I can see my output. Since these are all nothing but the various forms of waveforms. So this is a rectangular waveform. This is a Smith chart plot. This is a polar plot, and this is a table format. So I can go and click the rectangular format, and as soon as you click on that, this window will come. It will ask for what output parameters you want to plot as a graph. So I want to check the S11 means I'll click on S11. I'll click on that, and if that is let it be in dB, because always I try to find the S11 in dB. Give S11 in dB. Okay, I'll go for another graph of marking what is S21. That also I'll put it in dB. So if you see here, exactly you see the graph. My design frequency is what? It's 5 gigahertz. So I'm getting a very good dip at exactly at 5 gigahertz. And go to marker, click new marker, place it exactly the value and bring down this inside. Similarly, you place another marker at 5 gigahertz here. So you see what all the results we have got. So my return loss is minus 32 dB, which is very good. If it's going greater than minus 10 dB only, it's very fine. And here S21, if you see, that is 0 here, it means my insertion loss also is very less. Whatever input I'm giving, it's properly going out. There is no much loss. And you can even see S22 also. You just click on S22, let it be in dB. Okay, you give, come down, and you see here again this also is giving me the same value. So I've designed a very good matching network, which is matching both the impedances. One impedance is 50, the other impedance is 100 plus j 10. So this is nothing but my simple experiment which I can do with lumped matching circuit. So how to, this values of C and L are directly taken now from this Smith chart tool. When you keep it over here, that values will be showing. But now I'll show you in one more video how we can do this with theoretical concepts also. How we can use, which formulas we can use to calculate this with the Smith chart we can see in the other video. Thank you, students.